Thank you.
Thank you.
Yeah, now it's time to talk about timing. So this remaining sessions are dedicated to this topic. My name is Jörg, and as I said, I'm from Oscilloquartz. I'm here with Frederic, and we want to talk a bit more about timing. And before I start, I would like to tell you what happened to me a couple of months ago. Back then, a partner of us were calling me on a Sunday afternoon, of course, and he was telling me that he was contacted eventually by a mobile operator out of that region. So later on this Sunday, we had a call with the engineering team and the CTO. So this topic has escalated quite high up. So what happened? They experienced some issues with the GPS timing servers, and that actually impacted negatively their mobile services. And the reason for this was the tensions between Israel and Iran. And GPS is owned and controlled and operated by the US militaries. And they decided to switch the GPS signal off or partly off. So now I remember that I should not move further to this side. So the impact was clear, no GPS signal or partially not available, and the impact was also clear. The mobile operator could not offer the services to their subscribers, and the subscribers were eventually complaining. So with this title, we want to look at what GNSS means, the Global Navigation Satellite System. So some of you probably know it, but we want to touch quickly for what we use it here on Earth for P&T, position, navigation, and time. And we also want to look at what are the potential threats to it, cyber attacks, for example. And now we make the point towards how that is important for our critical infrastructure. And by one, for sure, data centers are a critical infrastructure and becoming more and more critical. While we have heard today AI, big data, virtualizing the data centers towards the cloud, and this is not going without exactly precise timing and accurate timing and stable timing throughout the data center infrastructure. Okay, now I need to take this point here. Next. So Oscilloquartz is being in that business for quite some time, so some background to the company. And we do R&D in Finland, in Switzerland, and also in Israel. And I'm especially proud of our R&D on our cesium clock technology. So we are one of two companies which developing cesium clocks, and that's being done in Switzerland, and also the production is done in Switzerland. And we have got a lot of funding also and support from the ESA in order to do that, to productize eventually after a couple of years of development, cesium clocks. So this is a critical element of our timing sync infrastructure in order to provide robustness and resilience through critical infrastructure, and we will learn about what critical infrastructure means. So Global Navigation Satellite System. That's what we have in orbit. GPS is up there since the 80s. Or even earlier, and in the 90s, the US government decided that this service will be made free to all the people on the globe. And then, I mean, the situation or what has happened, so we all know how to use the GPS on our mobile phone, in the cars, and so on. So without this, our life would be completely different. The next is Galileo, and this is a European one. It's being built by the European community. It's not controlled by the militaries like the GPS. So that what happened in Middle East can certainly not happen in Europe with Galileo. And to all the systems we are now having here available, but there are more like GLONASS and Baidu in China, GLONASS Russia, and the more regional ones are also available. So there is a lot of attention given by countries to be somehow able to provide these systems, even if it's only regional. But to all these systems, there are some pros and cons. And what is good? It is free. That's why everyone is using it without any problem. But there is no service guarantees to it. whether it's available or not. It's not on us, it's basically on the system itself. And we have to think about some vulnerabilities. One are certainly the cyber attacks we can consider, but there could be many more, like that what happened in the Middle East again, or maybe there can be some maintenance problems bringing the services back while there were some software updates and so on, which happened. And then there's also the weather, and there's the sun, which can also impact the service availability. So looking at the enemies, then we can differentiate between jamming and spoofing. Jamming is fairly easy. You just need to have a transmitter which is transmitting in the same frequency bands, and then you blank out the signal. The information will not reach the receiver anymore, and the receiver subsequently will not be able to work in a way it's supposed to work, mainly providing the timing information to our critical infrastructure, be it mobile operators, be it power utilities, be it in a data center. The other one, spoofing, is a bit more complicated to do and also a bit more complicated to detect. And but this is happening as well. And the way it works is that it takes the signal, manipulates the signal, and sends it on to the receiver. So the receiver, in some cases, is not realizing that he gets fake signals, continues to provide the services to the underlying network, and all of a sudden you are away from the time you used to think it's actually the time on your systems. And usually you want to trace it back to UTC time. So with this, I want to highlight which critical infrastructure is actually relying on precise and accurate timing. And this is part of the NIS2 directive, and this is a EU initiative. There used to be another NIS some couple of years ago, but more details on that later. And we see also, this is taken from one of the OISPA reports, how many GNSS satellites and GNSS devices using still the GNSS signal to provide timing and sync information through their infrastructure. So this is actually showing the importance of time where we use primarily GNSS as a source throughout these critical infrastructure we have identified on the right side here. So we have to do something in order to mitigate the vulnerabilities we see today with GNSS. So let's make an example and take the data centers here, for example. Data centers usually have servers, timing servers throughout their data centers. Used to be in the past NTP, but we know more and more that NTP is not providing the accuracy today's data centers are requesting. And this is due to the fact that we're virtualizing data centers, the servers, the applications across different multiple data centers. And also when we look at AI and big data, they all require precise time in order to correlate eventually and to make AI, for example, also more efficient. Simple examples here on that is, what I wanted to express is that simple read-write processes, if they are not synchronized across the servers, then what is happening, the data integrity is not given and retransmit may happen. So the retransmit will then put additional load on your bandwidth you have purchased, and that also means more power consumptions because the server need to retransmit. This is another negative impact on if you do have wrong timing in your data centers or maybe even spoof timing. But Frederic will give you some more example now when it comes to data centers.
Thank you, Jörg. Good afternoon, everyone. So my name is Frederic, and I'm going now to discuss a little bit about the evolution of the timing accuracy required for data centers. So as Jörg mentioned, we are transitioning from millisecond to nanosecond. The reason is the following. Currently, we see an augmentation, tremendous augmentation of the amount of data. Every data need to be timestamped, having a deterministic information, so you can trace the vulnerability or the issues that you can come. But it's also very important because it's also in place for regulations. So NIS2 is one part of the regulations. But it's also in place because otherwise all the operations will be frozen at some point in time. Nothing will work. So we'll be completely stuck, frozen, and completely blind. And so this is such a small thing that nobody is really paying attention, but this is critical. So why are we going there? So millisecond means that we are using a protocol called NTP. It provides a millisecond accuracy. We're going now to use another protocol called PTP, using the same network, but going to nanosecond accuracy. What are the results? So some key companies made actually the test. So companies like Google, NVIDIA, Meta. So they are increasing the level of accuracy by 100. The result is they saw that that distributed database network throughput has been multiplied by 3. Or so to say, it means that by increasing the level of accuracy, they were saving money on GPU because in order to cope with the latency, you need to put more power on the GPU for the servers. So put some money into your timing accuracy infrastructure and you'll get some results. It means that when you have millisecond accuracy, the oscillators which are embedded with the time servers, we call these crystal oscillators or rubidium. In case of GNSS outage, meaning if you lose the GNSS for solar flares or from atmospheric conditions, or for jamming and spoofing like Jörg was commenting, it just means that you need to maintain the continuity of the timing service all the time. It cannot stop, it cannot fail. It's like the electricity. The blood and water vein in our heart, it cannot stop. So basically, if you maintain it properly, you need to have all-over coping with that. At millisecond accuracy, a crystal oscillator rubidium can last it from weeks to months. But what happens when you go to nanosecond accuracy? The same oscillators, crystal and rubidium, can last for hours up to a day. Is it enough? It's not. So there is one technology allowing you to maintain it from 100 nanoseconds up to 100 days, and this is what we are currently having. This is called cesium clocks, and being more precise, optical cesium clocks. And with this, you will have two advantages. First, you'll be able to provide the all-over capability that your data center is requiring, but you will be also able to be completely free from any interferences coming from the GNSS, because by design, you will have an instrument, a system allowing you to maintain the accuracy for a durations of 100 days at minimum.
Yes, thank you, Frederic. So let's move on what we can see with regards to critical infrastructure and what is coming also from the European Commission. And that's being presented a bit here on this slide. So we discussed already the NIS, Network Information Security number 2. There was out something already in 2016. The difference between the two is that those running and operating and that are responsible for critical infrastructure are now made accountable for not introducing correct measures to protect the system from failures. And there's another one called the Critical Entities Resiliency Directive. And this is specifically going to identify critical entities like a timing server in a critical infrastructure to be deployed in a way that it can resist any kind of attacks. So the European Union gives already some directives, and this need to be implemented throughout Europe, country by country, to translate this into national law. So there is already something from the administrative point to consider in case you're going to operate a critical infrastructure according to the list you have seen on the previous slide. Not only that there is this directives, we also see now on the next slide what can be done in order to protect or to complement the PNT, we going to, of course, today use from the satellites. Also, EU, the European Union, with the European Radio Navigation Plan, provides information what to do for those operators. And why we see this is actually a nice diagram. So it shows from the top the GNSS being the system delivering timing towards the various users, while at the same time, it's not coming across very well, that we have with this green bar on the bottom, a fiber optic, a terrestrial infrastructure in place to disseminate timing from a central source. So this central source can be, of course, the National Metrology Institute. So similar to what Netnod actually is operating here across the country, could also be perceived to be a solution for a more closed environment, like a couple of data centers or a power utility or mobile operators. And in fact, for mobile operators and power utilities, we're seeing already that they taking on this approach, deploying their own time clocks in the network, distributing the timing information from these core time clocks throughout the network to their endpoints in their network in order to synchronize the applications like for the grid, the elements to control the grid, monitor the grid, and so on. And also interesting is that in this document, references are being made to the SEER and the NIS2 again. So they are interlinked with each other. So it gives you a good foundation to, in case you want to prepare your infrastructure according to these guidelines given here. So when we look at the alternatives or complementary PNTs, we of course have the satellite-based and the terrestrial-based, as just explained. From a satellite point of view, we have Galileo as said, and Galileo comes as a what we call open service. So this is available for everyone on the phone, in the car, and so on. There's also another service available, which is more protecting the integrity of the signals. So it's a bit more protected against spoofing attacks and to some extent jamming. And then there is another service called Galileo Public Regulated Service. And this is a service which are probably being used by defense, by some governmental organizations, by the fire brigade, by the police, and so on. So this is very much close to a certain group of users. And we want to build for all these type of constellations timing capabilities in our devices. So then we have EGNOS. This is being in place since many years, even before Galileo was brought up into orbit. This is mainly used by, for example, the aviation market. And then we are now having a lot of talks about low Earth orbit satellites and constellations. Also, the European Union is thinking about bringing their own low Earth orbit satellites into the orbit. But we do have already a constellation up there, and that is called Iridium. Iridium was built in the 90s. Initially, it was for voice call and simple data messaging. Now they have enhanced the capability of these Iridium satellites to give you also a timing signal from these low Earth orbit satellites to us on Earth. And when you have the right receiver technologies in your devices, you can receive that. So the benefit of these low Earth orbit satellites is that they come with much stronger signal strengths. So they're hard to jam. They're also encrypted, so that is also difficult to spoof. So it gives you another alternative to, for example, what we get today from Galileo. Yeah, excluding what we get with Galileo Public Regulated Service. When we look now at the terrestrial complementary PNT approach, then we need to look at cesium clocks, as Frederic already mentioned. So cesium clocks have been developed already sometime in the mid of the last century. by a couple of guys, and also Oscilloquartz was one of the first looking at this technology, and they brought up a first cesium clock in the 90s, and the first customer actually was in Norway. So since then, our product portfolio has developed far beyond these half-rack, telecom rack, big monster of a cesium clock. So now they are more or less a 3-rack unit high device commercialized for various use cases. So we differentiate still between some legacy type of cesium clocks, which are called using magnets, magnetic deflection, and now the next generation where we have really some unique position with is the optical, what we call optical cesium clocks. And what is optical in this clock is that we're using highly precise and stable laser technology to control the cesium atoms, and that is the difference to the magnetic deflection, where we just throw away all the atoms which we cannot use for the calculation of the frequency. With the lasers, we bring energy into the atoms to change the state, so that we can more or less use all the cesium atoms. So we get much more efficiency out of the cesium clocks. Okay, with this, we have now a various type of cesium clocks, from high performance to super high performance. We will soon have a version which we call then ultra high performance. Not want to go into the details and what are the typical characteristics when it comes to the performance. We also go and have more price performance optimized versions, which are called then the 3200 series. These are devices which gives you a stable frequency, that's all. And now we need to combine this with something which can maintain time. And this is an ordinary timing server, can be used for NTP, PDP. So we combine the two systems together, and we get initially the timing information from the GNSS, but can also, as it's been showing in this diagram, from any other source, while any other source can potentially be your National Metrology Institute. So you feed in the time, and then the system runs on its own as what's called here the core time clock. And so now, whenever the source of time, GNSS or the external from your National Metrology, if that input is failing, then we can still run what we call hold over the clock very precisely over a couple of days, weeks, and even months. So depending on which type of cesium you select, it can be from 30 to 50 and even 100 days, keeping the same accuracy with a very low drift, and so supporting critical infrastructure as we just have discussed. So how would such a system work or look like a bit in an abstract manner for data centers? So that means we have at least two cesium clocks, core time clocks together, being built together for data centers. So they are in various locations in operation, and then you use a fiber optic link with perhaps a white rabbit as a transport protocol for the timing, and then you distribute the timing information across your connected individual data centers. So this is a system in place allowing you to run very agnostic timing across your own infrastructure. Of course, important always to have control of what's going on, and with this you need a good management system, and that's also what we have here in our portfolio. Not only that it manage the alarms and configuration activities, it can also do proactive performance management, so that you see that in all time, during days, weeks, you deliver the timing in the accuracy you want to have it. And that is very important. But you also can now, in addition to that, we can also enable the monitoring of the GNSS receivers you have in your network. so that you see at any point in time whether there are jamming and spoofing attacks on the various locations you have to monitor. Some of the interesting safety bulletin I have read recently was given by the European Aviation Safety Agency, and they were recommending to their members that they should have some active monitoring capabilities at their airports to monitor jamming and spoofing attacks over the period they want to monitor that. So it's a very critical element to detect and eventually then also report what is happening on your critical infrastructure. And I think with this I'm done with my presentation. I hope it was somehow useful and informative, and thanks for listening.
Thank you so much. We have maybe time for one very quick question if there's anyone with a question. Otherwise, let's thank them for the presentation. Thank you very much, guys.
Thank you.
Thanks.